Good morning or afternoon, maybe even evening. This is day 6 in the 5th unit in calculus, and today we're going to be looking at related rates. Okay, yesterday or last day, you probably did some practice dealing with the distance problems that we had. Okay, hopefully you tried a few of those. So we're going to now go into related rates, and we're going to be going into different kinds of shapes of related rates over the next little while. We're going to do spheres, cones, cylinders, and then at the very end we'll probably do motion, like movement, and those will be all the related rates problems, and that'll end the unit that this is. And this is again, as I mentioned earlier, it's one of the more practical units that we're going to be following. Lots of word problem type things. So as we wait for the Blackboard to pop open, let me pop open my notes on the other side here that we're going to follow today. And what we'll do is we'll define what a related rate is, and then we will spend some time just looking at sphere problems. There's a few different types. With spheres, you can talk about the circumference and the surface area and the volume. So we'll look at each of those three types of related rate problems when we get there. Okay, so looking at where we were last time I did this, was around the end of April when that last time I taught this. So we're right around on track. This would be, I've got this one scheduled in for May here, beginning of May. So we're right around track in terms of time spent. And I'm going to try to finish this calculus course up early in June, mid-June if I can, so that we have time to do a little review and that you have some time to write the final exam. And I have time to mark it as we have quite a few people in it this year. Okay, so this is day 6. And this is unit 5. And what we're going to be looking at today is related rates. Not spheres. Okay, and what we're going to do today is what is a related rate? And after that, we're also going to be looking at example sphere problems. Okay, and in there we'll look at circumference. Okay, we'll also look at surface area and volume. And then we'll do some practice either today or tomorrow, depending on how time goes with the course. I only have 4 sphere practice questions. These are not too hard. So in terms of what is a related rate, sorry, what is a related rate? Okay, oops, that's a little small. Let me make it bigger. Here's a definition that I copied from when we did it last. There we go. So related rate problems, which is what we're going to do, these involve changes with respect to time. Okay, so you're going to be, if you're doing a volume question, it'll be like centimeters cubed per minute or second. Or if you're doing a surface area question or area question, it'll be like centimeters squared per second or hour. If you're just doing a straight speed question, kilometers per hour. Okay, these rates of change can be expressed in calculus notation. So that's the way I'm going to start, is I'm going to give you how we express a related rate. Of course, I'm going to have to use the marker because it's going to be as a derivative type expression. So remember when we were talking about derivatives represent a slope, okay, on a curve. Okay, so that slope is something over top of something else. If you remember, slope is rise over run. Okay, and a rate is the same kind of thing. It's a quantity over time. So we can use calculus derivatives to express rates of change, okay, or rate type expressions. So in calculus, we write it like this. Let's get the marker out here. Okay, so if I was talking about the change in area, I might write it as dA dt. Okay, so these are all going to be with respect to time. With respect to time. And this would be area over time. Okay, and the unit for that would be something like centimeters squared per second, or centimeters squared per minute, or whatever, depending on what you have in the question. Okay, and that would mean, for example, if you had a balloon and you were blowing it up, okay, as you put air into it at a speed, as you increase the volume would be increasing at a rate. It would be blowing up at a rate, and that's where the volume would be growing up around the edge of the balloon, right? Surface area of the balloon would be getting bigger. The volume of the balloon would be getting bigger. And all you'd be doing is blowing in air, which would be a volume. But then the radius of the balloon as well, the measurement from the center of the balloon out to the edge, would also be changing. So there's 3 different variables in there with Saphir problems. Okay? So you could also have area, like I said. You could also have radius changing. So we would write radius as dr dt. That means the radius changing with time. Okay, and that would just be, radius is a length, so that would just be like centimeters per second. And the third one we could get is we could get the volume, as I talked about, with a Saphir problem. So we go dv dt. Okay, and this would be volume over time. And this would be like the air that you would be blowing in. You'd be blowing in a certain amount of air. So that'd be cubic centimeters over seconds. Now you could do it per minute as well and stuff like that, but you have to make sure that the units kind of match up in the question. Sometimes you have to convert from seconds to minutes or minutes to seconds, sometimes centimeters to meters, making sure all the measurements are the same. Okay? So those are the 3 rates of change that we're going to use in Saphirs and expressed as a calculus derivative. Okay? And this is where we use the two fractional type derivative notation, because it helps us with understanding area versus time, radius versus time, volume versus time. Okay, so we will be looking into at the shapes and how they relate to different measurements with a sphere. So we have to know all the circular and Saphir formulas to use in this Saphir problem area. So let's do that next. So we need to use, we will need to use Saphir. I'll put the H there first. And circle formula in related to spheres solve these problems. Okay, so you don't have to memorize these. I will put these on a formula sheet, but what are the sphere formulas that we're going to have to use? Well, volume of a sphere, 4/3 pi, remember pi is a number, r cubed. R is the radius. That's the volume. Surface area, which I like to call SA to make sure that we know it's surface area, that's 4 pi r, oh, not pi to the r, sorry, pi r squared. 4 pi r squared. And you'll notice the relationship between the two if you're thinking calculus, right? Derivative of this is just this, right? Okay, and we also need to know circumference of a circle. So these are circle ones, 2 pi r times d, or if we know that d is 2 r's, we could write it as circumference equals pi times 2 r's, which you'll notice that represents the circumference around the circle. Okay. And then we also have the area of a circle equals pi r squared. So the area of a circle circumference of the circle okay, and this is the surface area of a sphere. This is the volume of a sphere. So those are the formulas that we'll need in our questions when we work them through. And they look, it may seem like, oh, what are we doing here? But once we actually do an example here, it'll start making better sense to us. Okay, so let's do a simple example, kind of like this balloon one here. Okay, so let me dig one up here. Okay, so let's say that we're just going to blow up a balloon. We'll do this first example on the next page. Okay, so this one I'm going to cover all three formulas in it. Okay, so let's say you are inflating a balloon. Let's do an example here. Inflating you're inflating a balloon so that the radius is increasing at a rate of 2 centimeters per second. Okay, so that tells us the radius is growing. When the balloon has a radius of 4 centimeters. So you have to at a specific time. Get 2 L's in there. Oops. Okay. Find. Okay, knowing that you're blowing up the balloon and at 4 centimeters of radius, when it's at that spot, you're blowing, the radius is growing at 2 centimeters a second. Find out how fast the circumference of the balloon is growing. So circumference will still be a measurement. Okay, now we didn't put a circumference one on the last one, dc dt, right? I didn't put dc dt here for circumference, but we could use it, right? Oop. Okay, how fast is the surface area growing? Okay. And the last one, how fast is the volume growing? So we'll do all three of those. There we are. Okay, so the first thing is we should write down what we know first. So as we're solving this, we know already the radius is increasing. Okay, so we know dr dt. The radius is increasing at 2 centimeters a second. When r equals 4 centimeters. Okay? And we're all looking at a specific point in time when it's 4 centimeters. After that, it could change because you could slow down or speed up. But let's just say that you were doing that and you wanted to find it out at 4 centimeters. Okay? So that's what we know. Basically, that's it. But we also know what the circumference of the sphere is. We also know what the surface area of the sphere is. We also know what the volume of the sphere is according to formula. So what we do is we take a look at, for number A, we look at the formula for circumference. Circumference equals, let's write it as 2 pi r. Because we want it in terms of r, because we have an r rate and an r specific time. So all you do is you now take the derivative of it and derive every little variable. Remember, pi is not a variable, right? Pi is a number. So this is a variable and this is a variable. There's two variables here, okay? So what we do is we take this and we go dc dt. We want the circumference rate change with time, which we do know is going to be dc dt. And that's, now we take the derivative of this with respect to r. So if you're thinking about it, 2 pi is just a number, so it stays there. The derivative of r is 1. And then we add in the dr dt. The radius change. So this is the expression. The rate of change of the circumference will equal 2 pi times 1 times the rate of change of the radius. And that's basically what it means. And we don't notice that we don't need to use the r in this case, but you'll see we'll need it later. So what we do is we go, well, dc dt, the circumference rate of change, is equal to 2 pi times 1, which we're just going to leave out, and then we put in our 2 centimeters a second. So our answer then is going to be equal to 2 pi times 2 is 4 pi, right, centimeters per second. And that's our rate. And if you like it in to the nearest tenth, pi being 3.14, you can write it like this: 4 times pi. Okay, so I'll just put it in the calculator. And that's 12.56, so 12.6 centimeters a second. If you change the pi into the 3.14. And that's as simple as it is. Pretty simple with the circumference, because the circumference is a really simple formula. Let's try this one. how fast is the surface area growing? So surface area, if we remember, for B, surface area equals 4 pi r squared. Okay, so there's only, we want DSA, I guess you could just use area there, but we'll go DSA because I put SA down. The rate of change of the surface area over time. Okay, and we take the derivative of this r because we have dr dt given to us. So the derivative, remember 4 pi is just a number. Okay, remember pi is just a number, it's not a variable. Okay, the derivative of r squared is 2r to the power of 1. Okay, 2r to the power of 1, and then we add in our dr dt. We have to multiply it just like when we're doing implicit derivatives. Okay, so there's the expression for surface area. Okay, we can simplify that a bit. 2r times 4 pi is 8 pi r. Okay, I should put the variable in there. Sorry guys, let me do this. Let's go dsa over dt. We should keep that in there so we don't get confused. Okay, and then it's 8 pi r times dr dt. Now you see why we needed that 4 centimeters to be able to calculate it. Okay, so now we just plug our variables. We know what this is and we know what r is. So dsa, and we keep our units, over dt. It's going to be 8 pi. Remember, pi is just a number. R, well, we want it at 4 centimeters. dr dt, 2 centimeters a second. So we're going to get a unit that's, we multiply that together, we're going to get 2 centimeters on top and 1 second on the bottom. That's centimeters squared per second, which makes sense. So 8 times 4 is 32 times 2 is 64 pi. Okay, centimeters squared per second. So that's DSA. That's how fast the, let's move that up so it's not in I'm not blocking you off. Okay, so that is how fast the surface area is changing. And if we want that as a decimal to the nearest tenth, we'll say, you just go 64 pi on the calculator, which is 201, we'll say, centimeters squared per second. And that is as simple as it gets. Okay, let's do the volume one next. Okay, the volume one is the exact same thing, except now we're going to be dealing with the volume formula rather than the surface area or circumference formula. So we'll extend our page here. Okay. Oops. Okay, so in C, we're going to be using the volume formula. Volume of the sphere is 4/3 pi r cubed. Okay, so that has the r in there. Okay, we have to take the derivative of this to get dv dt. The rate of change of the volume is going to equal, okay, we have to take the derivative. So we have to take 4/3 pi times 3 r squared, and then we got to add in the dr dt, just like we're doing implicit derivatives, because there's more than one variable here. Okay, and then we can simplify that down. dv dt. Okay, 3 times 4 divided by 3, the 3's will cancel out. So we're going to end up with 4 pi, cancel that and that, r squared dr dt. And there's our related rate expression. Okay, and then we're going to have to plug in our numbers. We know what r is, and we know what I'm just moving this down. There we go. We know what r is, and we know what dr dt is. So we go plug those. Plug those in. So dv dt will equal 4 pi r squared is 4 centimeters squared. Okay, remember that 4 centimeters? That was, okay, square the whole thing, times 2 centimeters per second for dr dt. So, okay, if we multiply all those together, we've got 4 pi times 16 centimeters squared times 2 centimeters per second. Okay, so we're going to multiply all those numbers together now. 16 times 4 times 2 is going to give us 128 pi centimeters cubed per second, because we got 3 centimeters on top. Okay, or if you want to take it down to the decimal, what is that? Well, it's twice what we had before, so 402 centimeters cubed per second. So this is how fast you're inflating the balloon at that particular time. This is how fast the surface area is growing at that particular time. And this is how fast the circumference is growing at that particular time of 4 centimeters. Okay, sphere-related rate problems are the easiest type because they only have the variable of r in them, the radius variable, okay, related to one of the other quantities, surface area, volume, circumference. Later on, we'll do some other ones that have other variables in it, and they get a little more complex when you have more variables, so we'll save that for next day. So we're about 20 minutes, let's see where we are here, 27 minutes in, so I'm going to leave some practice time for you, but I want to try one more to see if you're getting it or not. So let's try a little bit different. Okay, let's move this. Let's try one. Let's see what I got here. What if I give you the rate of change of the circumference rather than the radius, and you have to find the volume? That kind of question. Let's do one like that, and then we'll give you some practice to do. All right, so this one will be another example, but this is going to have the circumference. Let's say a beach ball is being inflated at 20 centimeters per second, of growth to its circumference. Okay. When the diameter, so I'm careful here, I'm giving you diameter, not radius. When the diameter is 30 centimeters. How is the volume of the beach ball changing with time? Okay, so let's try this one. So this is a bit tricky because you're given circumference one. So you're going to have to change it into the radius one. Okay, so what we're given is what we're going to write down first. We know that dc dt is 20 centimeters a second. And we know that d, or 2r, because the diameter is 2r, equals 30 centimeters. Okay? Okay, so we have to change, because volume is dV dt equals 4/3 pi r cubed. Because of the r, we have to change dc dt into dr dt, because we need dr dt for this r. The circumference is not in the volume formula. Okay, so that's the first thing that we're going to do. Okay, so let's do that. So the circumference formula is equal to 2 pi r, right? R, we know that r is going to be equal to 15 centimeters. We need it, right? Because 2 pi equals diameter, or 2r, pardon me, equals diameter. Okay, so then we take the derivative of this, dc dt equals, okay, derivative is just 2 pi times 1 times dr dt. Okay, now we're going to solve for this. So this is 20 centimeters a second equals 2 pi times dr dt. Okay, so we just simply divide both sides by 2 pi. Okay, so 20 centimeters divided by 2 pi. Okay, so we're going to round this one off to the nearest tenth. So 20 centimeters over 2 pi. Okay, we're dividing out the 2 pi here over there. So 20 divided by 2 pi. Okay, on the calculator, you get 3.18. So we'll say 3.18 centimeters, or we could go 3.2 centimeters a second. That should be good enough. Okay, so change it into that. Second step now is to do the dV dt now that you know this one. dV dt, that's going to give you 4/3 pi times 3r squared dr dt. Okay, so 3's are going to cancel out. It's going to be multiplying these all together. We're going to get 4 pi r squared dr dt. Okay, now we got to plug in the 15 there and the rate of change, 3.2 centimeters a second there, to get our answer. So we end up getting 4 pi times 15 centimeters squared times 3.2 centimeters a second for dr dt. Now we just take our calculator out. We'll go to the nearest tenth, I guess, or maybe the nearest whole centimeter cube, because it'll be in the thousands probably. So 15 squared times 3.2 times 4 pi. Okay. We get 2,880 pi. That's what my calculator tells me. But if we want it in decimal form, it's about 9,047.7. So 9,048 cubic centimeters per second. Okay. So let's just double check that one here in case I didn't multiply right. I don't have anybody here helping me to check it out. So 15 squared is 225 times 3.2 is 720 times 4 is 2,880 times pi is 9,048, we'll say. There we go. Okay, so it should be good. So we end up getting dV/dt is 9,048 to the nearest, we'll go to the nearest cubic centimeters per second. So that's our rate. Okay, and that's an example of Saphir problems. Now they're all pretty straightforward because they only have that one variable. You might have to do a little bit of manipulating around a couple of the formulas, but that's pretty much the easiest type of related rate problem that you'll get. Okay. Okay, so let's take a look at our time here. Okay, that's about 35 minutes. So we're going to stop there. I'm going to give you the practice sheet as well. So the practice sheet, I'll show you what it looks like here. So let me just bring that over here in a second. I just got to open it up as soon as it does. Got a little bit of a slow computer. So the practice sheet, you'll see in a minute here, has 4 problems and then 4 bonus problems. Now, again, this is Mr. Friesen's prep work that he did with it. So in the practice sheet, just do the top 4. If you want to do a bonus 1 or 2, you can, but those are types of questions that I probably won't ask on a hand-in or a quiz or something like that. Okay, so it looks like this. In a minute here, it's popping open. I'll bring it over. Okay, so here's some 4 questions. Okay, right there. And then there's 4 bonus ones as well. So if you do the top 4, you're probably good for today. Okay, and I'll post those online. And I'll post the answers as well, the ones that Mr. Friesen did as well for us. Okay, so that's what you can finish up today. And then next day, we'll get into the next related rate, which will be either cones or cylinders or something like that. Okay, let's get that back over here. Okay, and we will see you tomorrow.